So I'm at Princeton. So unfortunately, I wasn't here the past 2 days because I had to be in Princeton. There might be some overlap in what people mentioned before. So forgive me if I'm repeating myself. Let's see. So this is supposed to be a movie. Okay. I hope that my movies work. I see. I don't know. Oh, okay. Maybe we can press play. So this is supposed to be a movie of convection in the sun. Okay, I'll wait. If this doesn't work, I do also have.
I'm gonna load it on a second laptop. If you can continue, we can come back to it.
Okay. Well, if we only have to skip this movie, that's acceptable. But the other ones, it's a key part. So please imagine convection. This is as you can see, the surface of the sun is full of convection, different length scales, these very narrow lanes, broad upflows, and this is kind of trying to understand what's going on inside stars. Has been a major challenge in astrophysics. So Arthur Eddington, famous astrophysicist in the early part of the 20th century, he claimed that the deep interior of stars is less accessible than any other region of the universe. So he might have thought that this was the case in 1926, but we no longer think this is the case now. Because if this movie would play, you would see that if you look at the surface of the sun, that one was me. Okay. If you look at the surface of the sun, there's actually lots of small scale variations, which turns out they're associated with sound waves. So if you could move forward one slide.
1 second, please. I'm sorry.
Is it possible for me to just use my laptop? I'm pretty sure this
Absolutely.
would work on my laptop.
Let's get that set up in front.
Okay. Sorry. Yeah. Stop the timer. Yeah. Thank you.
While we're setting up, you guys could go to that URL.
No problem. Thank you.
Just give me a second and I'll push it up.
Okay, sounds good.
Use this one here.
Yep. Yeah.
Good. We got to see the movies.
Okay, I'll start here. Okay, here we go. Okay, we're back. So here's the movie, the beautiful movie. This is what everyone's been waiting for. So this is measurements of the surface of the sun, line of sight velocities, and you can see these fluctuations. If you take a power spectrum of this, so this is the power in those fluctuations as a function of the spherical harmonic degree L and the frequency. Red here is large power. You see that there are these ridges. These correspond to coherent oscillation modes of the sun. And using these oscillation modes, we can infer the interior structure using a technique called helioseismology. The idea is that you make some guess of what's the, say, density structure of the sun. So you need to specify density, temperature, pressure, etc. And then you ask, what are the linear oscillation modes? And then you can derive different oscillation modes with different frequencies, and you compare those frequencies to the frequencies that are actually observed to determine if this model was good or not. So using this, and also theoretically, we know that the outside of the sun has convection, whereas the inner part of the sun is stably stratified. The energy is transported via radiation, so it's known as a radiative zone. So what does convection do in stars? So what I'm showing here is a movie, and this is one of the important movies I really needed for this talk to make any sense. So this is a simulation that I ran. It's a 3D simulation of turbulence, of convection in the upper part, and then you're stably stratified in the lower part. For visualization, I'm just showing a 2D vertical slice, but you can see these cold blue plumes falling down and the hot red material rising. And the key thing here is that there's both convection up here and stable stratification down here. And this is similar to what's happening in the sun. The key thing is that you have both the convection and stable stratification. And I think what's going on at the interface is really important. So here what I'm showing is a passive tracer field being advected by the flows that I just showed. And you can see all this action going on in the convection zone, very little happening in the stable region. But if you look carefully at the color scale, you might notice that all these colors correspond to the same value. So what does the convection do? It really just completely mixes up this region. We've expanded the color scale so it's not so boring. Just to show that in another way, here I've reinitialized the passive tracer field to just be a Gaussian here, and then I'm going to release it. On the right, I'm showing the horizontal average. And you can see that as soon as it gets into the convection zone, it gets all mixed up. And then on the horizontal average, you see just a straight vertical line. That means that the convection just completely mixes things up. So as far as I'm concerned, convection mixes things, it's boring. The convection zone, just completely homogeneous. Adam earlier told us about some more detailed things like differential rotation. I'd call that like a higher order effect. Okay. So I'm really interested kind of what's going on in this interface region. And one of the things you might see is that there are waves here. So you have these internal gravity waves. Maybe some people here don't know what internal gravity waves are. And since my time is not moving, I have plenty of time to describe to you an extreme. Oh my God! I just lost 3 minutes like that. This is unfair. So okay, well in that case, in like -2 minutes, I'll describe to you how these internal gravity waves work. You have a stably stratified background. That's to say that you have a low density above high density. That's stable. If it was high density above low density, that would be unstable. You would have convection. So you're stably stratified. This is called a radiative zone in a star. You take a fluid parcel in the middle. You push it downwards. Its density is lower than the density of its surroundings, which is this. Thus, there's a buoyancy force upwards. It's going to rise, overshoot its original position. Now it ends up here. The density is larger than the density of its surroundings. There's a buoyancy force downwards, and it's going to fall and undergo vertical oscillations. So that's the internal gravity wave. And these waves propagate at frequencies less than the buoyancy frequency or Brunt-Väisälä frequency n. Something that Oliver talked about earlier is rotation. Adam also mentioned this. Stars are all rotating. Rotation is extremely important, and I'm going to completely neglect it. Okay, so we have a convection zone here, radiative zone here. This is a diagram of the sun. You get these internal gravity waves, which are propagating only in the radiative zone, which means they're very hard for us to see at the surface. So that's kind of maybe a problem, right? So the internal gravity waves are only down here, but this is only what happens if you have a star that's the size of the sun. If you look at a larger star, a more massive star, those stars actually have convection on the inside, and they're stably stratified on the outside. So these stars might be promising for finding internal gravity waves at their surface, because after all, the only thing we directly see on these stars are their surface. Yeah, that's a good question. So actually, in between, there's basically as you increase in mass from one solar mass, this outer convection zone shrinks, and basically when there's almost nothing left up here is by chance exactly when you grow a little bit of convection in the center. Okay, So basically, all stars have convection somewhere. If you go to lower masses, this convection zone encompasses more and more of the star until, for low enough mass stars, you actually have a completely convective star. Okay, so the sun is easy to see because it's close by, but luckily there are some new telescopes that have been put up over the past 15, 20 years, 10 years, 10, 15 years, that look at other stars really, really carefully. And I think the main reason for these telescopes is to detect oscillation modes around other stars. And kind of as a byproduct, they might be able to detect exoplanets, but no one really cares about those. And in particular, just last year, there was a new one of these satellites, which is explicitly looking at a lot of these massive stars. And one of the goals is to find these internal gravity waves. And indeed, this is an example of the brightness fluctuations that are measured from one example star. And if you take a Fourier transform of this, you see these coherent oscillation modes at the surface, some of which may be these internal gravity waves. Okay, so kind of I mean, I really have no idea how much time I'm supposed to have. Like, you guys aren't seeing this, but the time, it's like oscillating. It's kind of like a wave, really. But it says 7 minutes I have left. I'm going to tell you about how we can actually maybe learn something about convection itself by looking at these waves. So I want to consider a system where we can easily study both convection and waves. So just to recall, for a normal Boussinesq liquid, you have that the temperature and density are inversely proportional. So hot material is less dense than cold material. And something interesting, is very important for life, is that water is a very strange fluid and has this funny equation of state where the density is not maximum at 0 degrees, but instead at 4 degrees. So what this means is that if you took a tank of water and cooled the bottom to 0 degrees, kept the top at room temperature, so then you can think of this temperature axis as kind of being proxy for height. Between 0 and 4 degrees, the density increases with temperature, it increases with height, and thus you have convection. And between 4 degrees and room temperature, the density is decreasing with height, so you're stably stratified. So this is a setup where you can study both convection and stable stratification in the lab by just taking a tank of water and cooling the bottom to 0 degrees, which was exactly what was done by my collaborator Michael Lebals in this laboratory experiment. It's a small tank, quasi two-dimensional, 20 centimeters by 35 centimeters by only 4 centimeters in the outer plane direction. And this is very important because I'm going to later do a simulation of this, and the simulation is going to be 2D. So I'm really happy that he used a quasi 2D tank. So if you move this temperature probe up and down, you can measure the temperature as a function of height. You see that you have this approximately isothermal region down here at about 4 degrees. That's the convection. And then here, the temperature is increasing with height. That's where you're stably stratified. If you use this green laser sheet and put in tracer particles, you can use particle imaging velocimetry to measure the waves up here. And they are able to measure waves. The amplitude of this is about 10 microns per second. So it's really remarkable how they can measure these, but we know that they're internal gravity waves because they satisfy the dispersion relation. Okay, so now I'm going to do a simulation of this using Daedalus. It's a software package that I've helped to develop. I also want to mention one of the other developers, Keaton Burns, who actually wrote most of the code, and I think he might be listening in on Zoom. So thanks, Keaton. Okay, so this is the movie, the simulation that I ran inspired by this experiment. it might look familiar because Adam showed it to you earlier, but everything he said about it was wrong. So at the bottom, we're cooling because it's ice at the bottom. We're using this weird equation of state. So it's cooling, and the cold, buoyant fluid rises up. You have convection, and then you generate waves at the top. So now how can we understand the waves? Well, what we did is kind of use the Lighthill theory of wave generation. It was inspired by sound wave generation, but we tried using it for internal gravity waves. By the way, Lighthill said you can't use it for internal gravity waves, but we did it anyway. I don't know. We'll see. So the idea is that you take all the linear terms of your equation. This is the linear wave operator for internal gravity waves. So you have this linear operator, and then all the nonlinear terms, you just imagine that that's a known source function that was bestowed to you from the heavens, and then you can think of inverting this linear operator to tell you what the wave field is going to look like based off the source term. So psi z here is the vertical displacement associated with the waves. Now, the nice thing is that we just ran a simulation, so we can actually calculate exactly what the source term is from the simulation. So it doesn't need to come from the heavens, it just comes from the simulation. So we just solve this linear wave equation with the source term from the simulations, and if you do that, and just look at the waves in the stably stratified layer, I'm going to show this movie showing the vertical velocity in the full simulation, and then in this model simulation testing the Lighthill theory, and you can see that the two agree pretty well.
Okay, no, that clock is right, by the way.
Okay, good. Thank you. Okay, so it seems like this Lighthill theory works, even though Lighthill said that it wouldn't. So thanks, Lighthill. Okay, so now, what does this tell us about the convection? Well, if you recall, we have this source term, nonlinear fluctuations associated with the convection. It seems to kind of the solution to this equation gives the correct waves, so that's a good news. So now, associated with the linear wave operator, you can come up with a Green's function, and then use that to calculate the vertical displacement. Now, we don't really care about the actual displacement of the waves. We really want to know something like the kinetic energy spectrum of the waves. So we want to know what's the energy of the waves as a function of the wave number and frequency, and that's going to be proportional to psi z squared, which then is proportional to the source term squared, which is the convective velocity to the fourth power. So really, this wave spectrum is telling you something about the fourth order correlation of the convective velocities. So we've done some theory to try to, it's very heuristic. We basically forget about how it's like a fourth order correlation. We just break up into second order correlations, use something like some heuristic Kolmogorov sort of theory for what's going on, and you can make some prediction of the wave energy spectrum that you expect, and the key features is that the frequency should the flux in the wave should decrease with frequency to this power minus 13 halves, and should increase with wave number to some threshold wave number, like wave number to the fourth power. So we want to test this in a simulation. So this is a 3D simulation run by Louis Cousson, where this is like an amped up version of the water simulation that I showed you earlier. So you have a higher Reynolds number, 3D convection down here, you have waves up here, and we just calculate the power spectrum, and we actually find that this frequency dependence is approximately minus 13 halves, and the wave number dependence is approximately wave number to the fourth power up until some threshold that we understand. So it seems like this works, which is kind of a miracle. But what I think what we've learned from this is that the convection generates waves. It seems like you can describe the waves using this kind of fourth order moment of the convective field. And because of that, you can actually think of measuring the wave properties as being kind of like a thermometer that you put into the convection zone. And just by measuring something outside the convection zone is going to give you some interesting statistical measure of what's going on in the convection zone. So that's, I think, an interesting property of this problem. Thank you.
Any questions for Daniel? Why don't we start with Zach?
Thanks, Daniel. Really nice talk. Just a question about your factoring the fourth order moment into like a second order one squared, essentially. Is that a Wick's theorem argument there, where you're saying you think only the disconnected pieces are important, or is it just a dimensional argument where you're saying even though you can't calculate it, the connected fourth order correlation function, you think it has to scale that way because of?
It's not any argument at all. It's just out of convenience.
But I mean,
Yeah, we have no like actual justification for doing this. But I think you could be more careful and use, say, like a Wick sort of theorem and try to justify it using that. But we haven't tried doing this systematically at all. But other people have. So I think it's possible. But since we haven't, I can't give you too much insight.
right. I mean, could you not calculate the 4-point function directly from your simulations and see how well this works?
Yeah, that's another possibility.
I'm not sure if you mentioned what Rayleigh numbers and what Prandtl numbers you're looking at with your simulations.
Yeah, so this simulation, our simulation, these 3D simulations were problem number 1. The simulations of water were problem number 7. This is, say, really number 10 to the 9, whereas the water case, again, we just used the values from the experiment. It's something like really number 10 to the 7, somewhere between 6 and 7.
The very low Prandtl number of stars in general, sun, that will make a huge difference, won't it? I mean,
that's right. Yeah.
Give
So
you very different physics.
Yeah, I think it'll be interesting to look at how things change at lower Prandtl numbers. We've done 2D simulations at Prandtl numbers, not too low, but something like 0.1, yeah. And well, you get waves. We haven't looked at it any more systematically than that.
All right, back here.
Seat mic isn't working.
Srini, could you shut yours off?
Oh. Now it works. So what was Lighthill's objection to using his method for internal gravity waves, and why is it okay? Or if it is. I mean.
So I'm not very familiar with his objection, but I think one issue is that internal gravity waves are generated at much higher amplitudes than sound waves.
Okay.
So the efficiency of sound wave generation goes like Mach number to a pretty high power, I think maybe like 5. Yeah, 5. And whereas the internal gravity wave, the efficiency goes like Mach number to the first power. Mm-hmm. So for Mach number like 0.1, for instance, you're going to have a lot of energy in the waves, and I think he was worried that the waves would then feed back onto the convection. Now, since we use these convective velocities from the simulation already includes that feedback, so we're safe.
Okay, thank you.
Well, let's thank Daniel again.
So turbulence in universe is not so different from turbulence we see on Earth. For example, turbulent mixing happens in clouds, also happens in molecular clouds, stars form. Also, turbulent diffusion of cosmic rays is similar to turbulent diffusion of smoke. Turbulent reconnection of magnetic fields observed near the Earth also happens in the most energetic explosion in universe, gamma ray burst. Similar to atmospheric turbulence, turbulence in our galaxy also scatters light coming from deep space. I'm going to talk about a different effect of turbulence you see that turbulence connects diverse astrophysical phenomena. I'm going to talk about turbulent dynamo that amplifies cosmic magnetic fields. Our universe is magnetized. This is a simulation showing evolution of cosmological magnetic fields. Magnetic fields exist on all length scales, from this weakest field in this large scale structure of universe down to okay, does it work? Okay, down to the strongest field in magnetars. Magnetic fields induce fundamental astrophysical processes like Faraday rotation, polarization, and because of these different effects of magnetic fields, we have different techniques to observe and study magnetic fields. So these are the magnetic fields we see today. But in early universe, the primordial magnetic fields are extremely weak. The question is how magnetic fields have been amplified to become the magnetic fields that we see today. It is believed that turbulence is responsible for the growth and maintenance of cosmic magnetic fields. Turbulence, as we know, also ubiquitous in universe. It exists on all length scales in the intergalactic medium, intercluster medium, interstellar medium, interplanetary medium. As evidence that turbulence amplifies magnetic fields, we can look at the magnetic energy spectra measured in different medium over different ranges of length scales. And they all show homograph parallel spectrum. Well, in this conference, we know very well that turbulence, incompressible turbulence, has a homograph spectrum coming from the constant energy transfer rate along the energy cascade of turbulence. And now this homograph spectra seen in magnetic energy suggests that it is a universal process that turbulence amplifies magnetic fields in different medium on different length scales. And this turbulent amplification of magnetic field is called turbulent dynamo. Let's look at how turbulent dynamo works. Imagine a turbulent medium. Let's put a magnetic flux tube in turbulence. Then the turbulent motions would stretch this flux tube. If we have conservation of magnetic flux, and then we would, in the stretched magnetic flux tube, the magnetic field lines get intensified and amplified, just like what we do with pulling noodles. The key to turbulent dynamo is this turbulent stretching of magnetic fields. Here are more illustrations of this amplification of magnetic fields where turbulent stretching. And because we have an energy cascade of turbulence and the turbulent motions on all different length scales do these stretching motions to amplify magnetic fields.
On the left, it's with noodles. It's done with noodles, this dance.
This person is a turbulent eddy, and the noodle is the magnetic field, so they're stretching that. And more specifically, we can look at the induction equation that tells how the magnetic field evolves because of different types of fluid motions. It can be compression, expansion of the fluid, or advection. But for the dynamo we talk about here, it is the turbulent shear that perpendicular to magnetic field that stretches magnetic field lines and amplifies magnetic field. During this dynamo process, turbulent kinetic energy is converted to magnetic energy. So we can measure the magnetic energy spectra at different time during the dynamo process. And you can see that the amplitude of magnetic energy spectra increases with time, showing the growth of magnetic energy. In the meantime, the correlation scale of the magnetic field, which is shown by the peak scale of the magnetic energy spectrum, move toward larger and larger length scales. And also importantly, we see that indeed the amplified magnetic field follows the same homograph parallel spectrum as turbulent energy, just as what we see in observations. Okay, so this is what we know about turbulent dynamo, but this is only half the story. In reality, besides this growth of magnetic energy because of turbulent stretching of magnetic fields, there is always loss of magnetic energy because of different diffusion process. And in diverse, it is clear that this diffusion makes this turbulent stretching inefficient. It makes this dynamo growth of magnetic energy inefficient. In diverse astrophysical medium with different plasma parameters, the diffusion mechanism is different. For example, here is a list showing the plasma parameters in different astrophysical systems. These are Reynolds, magnetic Reynolds number and magnetic Prandtl number. Physically, they correspond to the turbulent stretching and magnetic diffusion. And you can see that in different astrophysical medium, their values really change drastically. And so, as a result, the diffusion mechanism and the dynamo behavior in different systems are very different. By contrast, on the other side, these are the values of these two parameters in dynamo simulations. And you can see that because of limited numerical resolution, their values are really in very limited ranges. So clearly there is a huge gap between dynamo in computers and dynamo in reality. We don't really know that whether we are studying apple to compare with orange in reality. To bridge this huge gap, we need a theory, a general theory, that can be applied to studying the dynamo in diverse astrophysical medium. We have worked on developing such theory. I will discuss a couple examples to see how this theory works in reality. Let's first look at partially or weakly ionized medium, which is very common in astrophysical environments. All these cold gas phases where stars form, protoplanetary disk, solar atmosphere like chromosphere, all these are weakly ionized medium. In a weakly ionized medium, the dominant diffusion of magnetic fields comes from the low ionization fraction. We can easily understand that in a weakly ionized medium, the coupling between magnetic fields and neutral gas depends on the coupling between neutrals and ions. If the ionization fraction is high, then the collisions between neutrons and ions are frequent. They are strongly coupled together, and we don't need to worry about diffusion of magnetic fields. But if the ionization fraction is low, then the neutron-ion collisions are not frequent. Neutrals are weakly coupled to ions. That means the coupling...
Someone on Zoom needs to turn off their mic.
Oh, yeah. So in this weakly coupled region, it means that the coupling between magnetic fields and neutral gas is weak. Then the diffusion becomes important.
Someone on Zoom needs to turn off their mic.
So then does this turbulent stretching motion that is mainly carried by neutrals cannot efficiently stretch the magnetic fields, and the turbulent dynamo becomes inefficient. In this weakly coupled region at a low ionization fraction, we have analytical theory. As one of the predictions of our theory, we found that this region, it has linear in time growth of magnetic field strength. This is square root of magnetic energy. The growth rate depends on the ionization fraction and turbulence parameters. This linear in time growth of magnetic field strength is a very unique feature. It only happens in the weakly coupled region at a low ionization fraction. So this is our prediction. To test this theory, we have carried out a supercomputer numerical experiment with two-fluid dynamo simulation with a low ionization fraction. Two-fluid means neutral and ionized fluids. All these factors of the simulation, high resolution here, 3-dimension, low ionization fraction, and two-fluid, all these factors together make this simulation extremely expensive. But it's necessary to run such an experiment to properly simulate the physics of the coupling between neutrals and ions. Okay, let's directly go to see the numerical result. From the comparison between our prediction and the numerical measurements, we see indeed in this weakly coupled region, magnetic field the field strength grows linearly with time. So now with this tested theory, we can apply it to studying amplification of magnetic field in weakly ionized medium. For example, we have looked at the magnetic field during the formation of the very first stars in universe. In most studies of the first star formation, magnetic fields is completely ignored because, as I said, the primordial magnetic field in early universe is extremely weak. But in fact, turbulence can be driven in this gravitational collapse of the halo, and this turbulence naturally amplifies magnetic field. Indeed, we found there is a very efficient exponential growth. You see there's how many orders of magnitude growth of magnetic field strength. This is because of this turbulence stretching of magnetic fields. But it also has non-exponential growth stages. And this comes from the diffusion of magnetic fields. That makes dynamo inefficient and has a long time scale. Note that this is logarithmic. And this non-exponential growth stage that depends on the ionization fraction of the primordial gas. And the primordial gas is weakly ionized.
But the degree of ionization changed during all this time. Initially, it was higher.
Yeah, I mean, during the star formation, all parameters should change. So in this, we don't consider the growth of magnetic field due to the compression. It only comes from turbulent dynamo because we only want to look at this effect. So this is about dynamo in a weakly ionized medium. I probably don't have time, but in a different scenario at the dice of a star, there's an explosion. We know that explosion usually drives a lot of turbulence, and this turbulence can also amplify magnetic fields. But in this scenario, we need to use our theory in a different region, which is nonlinear turbulent dynamo. And in this region, we have the not magnetic field strength, but magnetic energy grows linearly with time. The growth rate is a small fraction of the turbulent energy cascade rate. Why it is small? Again, because of diffusion of magnetic fields that makes it inefficient. But in this region, it is not the diffusion does not come from the ionization, low ionization fraction. It comes from the turbulent diffusion, or we call reconnection diffusion of magnetic fields. Okay, so I don't have time to go to details, but I want to say that the same nonlinear dynamo also happens in magnetic field amplification in cluster of galaxies and also in the large-scale structure of universe that I showed at the very beginning. Okay, so I want to make 2 points. First, turbulent dynamo is a fundamental process. The ubiquitous turbulence results in ubiquitous magnetic fields in universe. And 2, our theory can be generally applied to studying this important dynamo process in diverse astrophysical medium. Okay, that's it. Thank you.
Let's start with Blakesley.
Nice talk, Xiao. I'm curious, do these your analytic expressions, do they also apply in the case of compressible turbulence, or are they only for incompressible dynamo?
Yeah, that's a good question. So for compressible turbulence, we have all these days we talk about there is both solenoidal motions and compressive motions. And this dynamo, this stretching, only comes from the solenoidal motions. Of course, compressive motions can also compress a magnetic field, but that is not so efficient as the solenoidal motions. So if we have a compressible turbulence, if we really want to carefully study the dynamo, we probably need to do the decomposition to, yeah.
Oliver?
If I understood you correctly, you're saying that the magnetic power spectrum also follows the Kolmogorov k to the minus 5/3. I didn't quite understand the reason for that. I mean, there isn't a conserved flux of magnetic energy through the spectrum, right? You sort of made the picture with the spaghetti or the thing that it's kind of stirred on all stages. So there's more like constant injection or some kind of, where does it come from?
Yeah, so if you look at this, the evolution of the spectrum, I'm not sure I can go back to that, but yes, so the magnetic fields in the dynamo process, magnetic energy is lower than the turbulent kinetic energy. So it is being mixed up, it's being stretched further by the turbulent motions. And until it reaches equipartition between the turbulent energy and magnetic energy. And these equipartitions reach the scale by scale. So the dynamo is fastest on the smallest scale because the ideal turnover is the fastest on the smallest scale. So after reaching the smallest scale, equipartition at the smallest scale, and the next larger eddy takes over to further stretch the magnetic field and amplifies magnetic field on larger scale until you have equipartition on a larger scale. So you see the evolution that eventually you would have larger and larger correlated magnetic field, but below this correlation scale magnetic field, it's just MHD turbulence. So MHD turbulence, the magnetic fluctuations, and the turbulence both have the Kolmogorov spectrum.
Yeah, maybe follow-up question. Because we know the small scale dynamo, which is efficient, and the large scale dynamo is very difficult to solve. I don't want to solve it yet. So for your solutions, your equations, and also your observation, are you talk about the small scale dynamo only?
Yeah.
Or coupling both, inverse cascade towards left.
No, there's so all this dynamo I talk about is so-called small scale, which means it's below the driving scale turbulence. And Ethan will talk about the large scale dynamo.
Then my next question is observation. Are you sure when you compare the observation, is small scale or large scale?
Yes. So all the spectrum, we see that it's below the driving scale of turbulence in different medium. They are not necessarily to be really small, but it's smaller than the driving scale of turbulence.
Okay.
Yeah.
All right, a quick one from you on.
I guess similar line of thought. So why do you have equipartition? Why is it that you amplify magnetic fields until equipartition and you stop it there? Like, what is it? A balance between amplification and diffusion?
Okay. Yeah, so the energy source is turbulence. The magnetic energy, the growth of magnetic energy comes from the turbulent energy. So at most it grows to the turbulent energy. And also when you have the equipartition of energy, you have the nonlinear effect from the magnetic field on the turbulent motions. And that is in the MHD region that we know that you have the effects of magnetic field that affect your turbulent motions. It's not purely hydrodynamic anymore. Yeah.
All right, we'll take one last quick one for us. If you want to set up for the discussion, maybe.
Yeah, I also have a question. What are the units of your energy? Is it magnetic energy or kinetic energy? Because they have different units. You cannot have Kolmogorov spectrum with different units other than energy.
So I don't know. So the dimension is the turbulent energy is the kinetic energy per k, for the spectrum. And oh yeah, I understand your point. So for the magnetic energy, we use alpha velocity. So the alpha velocity squared or k. So that is for the spectrum. So there is a magnetic field strength in alpha velocity.
All right, and Alexei had his hand up as well. So
yeah, just a short comment on the connection between magnetic and kinetic parts. So the invariant which is conserved by the ideal system is the total energy. And so the system has cross terms which describe the connection between kinetics, the exchange of energy between kinetic and magnetic. So while the kinetic energy is larger than magnetic, magnetic gets amplified to the equipartition. That's the process. And when the system gets stationary, then you can see the constant fluxes of both kinetic and magnetic energy across scales.
all right.
Okay, so we had a very interesting session, very kind of multidisciplinary and multidimensional, and we heard about turbulence in many different environments, many different, what I said, extra strains. My own interest is how these extra strains affect the spectrum. So one thing which I didn't have time to show, I will show it now because I think it's important. There is an idea that on large scale, the turbulence in geophysics becomes geostrophic, and we have K2-3 spectrum, which is determined by the entropy flux. So if you take the spectrum which is coming from the studies by Lindbergh, and if you use the equation with entropy flux and you know what the spectrum is, you can compute the flux of entropy, and this is the number you get. It's in a very good agreement with QNSE theory because you can transfer it back into latitude, you will get 34 degrees. It's more or less where the spectrum was computed. Now, if you take another set of data, this is satellite altimetry data computed by Hatry in 6 or 5 different regions in the ocean. He ran the model and estimated the flux for every one of these regions. He got a number of 10 to minus 18. So there is a difference between 10 to minus 13 and 10 to minus 18. It's 5 orders of magnitude. The spectra are practically the same, but the spectra of entropy are very different. So I would think that it's probably not the spectrum, not the flux of entropy which determines the spectrum on large scales. It, of course, has some implications, and it needs to be studied a little more, but this is an important point which needs to be.
Are they computing the same thing? I mean, it's not very obvious just by looking at the two numbers that they're computing the same thing.
It's not the only example. I know other people usually don't show the spectrum of entropy because, I mean, the flux of entropy because they cannot connect this to the spectral amplitude. There is a problem with this. Besides, you may have double cascade. You may have direct and inverse cascade in the same situation. And how do you deal with this? What is the amplitude of the spectrum? Another thing is that we were talking about direct and inverse cascade and how to simulate it. But there are simulations when direct and inverse cascade can coexist. There is a very interesting example in the spectrum in the hurricane vortex that if you look, it was measured by people who fly through the hurricane. In the lower part of the vortex, after about 200 meters, they find direct cascade. If you go over 200 meters, it becomes inverse cascade. How do you simulate this, and what do you do with the spectrum there? Because the spectra also tend to go to -3. So what determines the amplitude of the spectrum? There was a issue, theme issue, I think, in physical review of physics of fluids, analyzing interaction of different wave number triads, which we haven't discussed yet. And it's becoming very interesting subject because what happens in flows with extra strain, the relative contribution from different triads may change. And the same will change when you change resolution in computations, because if you have more wave vectors, you will have different, you may have different kinds of triads, particularly if you have extra strains in the system. Luckily, we have at least two people I know who started this analysis in the 90s. It's Wally and Grisha. So I wanted them to talk about it and to introduce this idea to the audience. I think it will be very useful kind of a tutorial if we can do it in a short time. So I will yield my time to Wally and then to Grisha.
Thank you, Boris, but yeah, I'm not quite sure what you want me to do. I mean,
Well, triads, I'm also not quite sure what I'm supposed to. I wrote a book on triads, so I can probably summarize it.
Well,
you mean something?
I want you have a paper on the physics of fluids with several people, which shows that, for example, squashing of a flow in one dimension will lead to change of the energy flow.
Now I understand.
So this is what I wanted to, since we did the simulations.
But it's more questions here. Okay, so who is to do?
Well, I don't know if I have a picture if Wally wants me to show it on the wall on the board.
that would help if you want to get it started.
Okay, this is a picture from Sahuvic, you know, and it just shows this triads, and you can talk about it. Does it help?
Yeah, I mean, you're throwing us into the ocean in the middle of the turbulence. Well, so okay, so it's in 5 minutes.
You want 4?
Richard, do you want to jump in or?
Yeah, okay. Let me, because I actually no. Okay, my mic works. I want to make disjoint, highly provocative remarks, which are related to all the geophysics, but in a very disjoint way. First of all, k minus 3 you see everywhere, and most of what you see k minus 3 is not turbulence, or at least not turbulence in a way that we mean it by entropy cascade in 2D. In a sense, k minus 3 is a boundary between a flow which is smooth in terms of first special derivative of velocity exists, and non-smooth. So if you ask when your vorticity diverges on the spectrum, that gives you 1 over k cube. It's a boundary, right? So in a sense, 1 over k cube and everything which is steeper does exponential stretching. Okay? And in this respect, it's very often that what you see as k minus 3, namely some peak at low k, is actually some kind of a semi-coherent, locally large scale flow. And in a sense that what we did experimentally some time ago with Michael Schatz is that we just did a system in a fluid layer which was a clearly inverse cascade, namely it was driven by small scales. There's no other source of energy. After a while, it develops 5/3 inverse cascade, and then it develops k minus 3 at lower k. Then you look at it, and of course you see that there are some big vortex inside because there is an inverse cascade, and it fits some big vortex. So you filter it out, right? So you just average over many rotations, you get this coherent vortex, you take it out, you get 5/3 all the way to back. Then you can measure, of course, your third moment somewhere inside, and it would give you direct cascade because you mix large scale and small scale. So what I'm saying is that k minus 3, unless you have 2 or 3 decays of k minus 3, it's not necessarily direct entropy cascade. There are many things. You take elastic turbulence at small scales, which Victor Steinberg does, it's k minus 3. Because it's locally quasi-smooth flow. Okay? That's what I want to say. So in this respect, I don't think that Nastrom cage spectrum is what we see in a simple model of a layer. It's probably more complicated, and also this fact that it has this knee could be indeed related to weights, because 500 kilometers is exactly where waves must be of order of vortices. And on the other hand, you have 5/3 between 10 kilometers and 500 kilometers. But you have minus what people call -3 between 500 kilometers and 5,000 kilometers. That's it. 6,000 kilometers. Already on global scale. So it's always less than the decay. I'm very skeptical about this being called scaling or turbulence or whatever. So that's my contribution to this. It's less than 5 minutes, so you have 7 now.
Well, do you have another thing to say?
I switched off my mic, so
You can you switch it on now? Because I wanted to ask you about the one-dimensional spectra. What you talk about is a two-dimensional, three-dimensional spectra, but you can have -3 only in one dimension. It's a different kind of animal.
You can have k-3 because you have shocks, or you can have this type of spectrum in one system. You can have k-3 because you have an elastic turbulence. There are many different ways of k-3, but what I'm saying is that unless you have 2 decades of a scaling, just be careful, because just a large scale flow imposed on small scale turbulence give you a pile up at low k, which is very naturally fitted by k-3, and like hundreds of people do it. What made me kind of over skeptical about it.
All right, okay, thanks. So
I think that was part of your point too, right, Boris? Is that the k-3 that we see is not an inverse cascade. It's actually just more wave-driven, just wave turbulence, basically interactions between internal waves. So weak turbulence at high scales.
This is true. I think that you can have -3 spectrum and you can have direct and inverse cascade on the same scales, and you cannot really say what is going on under this -3. The only thing which I would like to note is that the amplitude of this -3 spectrum is really important, because in our case it scales with f square and nothing else. So you cannot separate it from rotation. I don't know about the cases of Grisha. If you know the amplitude, if you can relate amplitude to other processes, he's now doing something else. Grisha, can you say something about the amplitude of this -3 spectrum which you measured?
Well, it depends on what, because in our case it was clearly everything inverse cascade driven, so it depended on your bottom friction and or large scale friction, and depended on your what flux you put into the small scale driving. But it was clearly something like what is called condensation by fancy people, that you have inverse cascade which feeds large scale flow. And of course, in the atmosphere, you have global driving too. You have planetary scale driving, right? So of course, it also produces large scale flow. This large scale flow make this three-dimensional turbulence at the scale of 10 kilometers like almost planar, which kind of turns it into an inverse cascade. Because generally, you don't expect turbulence on the scale 10 kilometers to be given inverse cascade. But if it's in a large scale shear, it could. But it's apparently was just a large scale coherent part of a flow.
Well, so in summary, when you have -3 spectrum, it's not always direct entropy cascade, direct entropy flux, not only in atmospheric flows, but in other situations.
Boris?
Yes.
Don't forget, there is also large-scale dissipation at low wave numbers for the atmosphere through infrared cooling. So I think you should be careful about trying to fiddle with the amplitude. I am using it.
I'm so sorry.
There's a huge mic here.
This is true, but on top of this, you may also have beta effect, and you can have jet generations, and you can go to different regime.
The dissipation will affect the amplitude, the spectral amplitude on the low wave.
Yes, and dissipation which you are talking about is isotropic.
It's highly anisotropic, right? It's modified by.
In the model you put a constant, but of course in real life.
No. I mean, but in real life, it's modified by clouds. That's the biggest modifier. Right, the clouds are inhomogeneously distributed in the upper troposphere.
Okay. Anybody else can say something about it?
Could I make a remark?
This is about the other part of the session that had astrophysical, stellar physics kind of context. So it doesn't apply to all the things we have been talking about. It's very encouraging to see more simulations coming along, especially trying to ask questions about specific details which really had been ignored for a long time. On the other hand, one should keep in mind that the Rayleigh numbers and Prandtl numbers that are applicable to these flows are very different from the domain that one computes. And therefore, one shouldn't really make too many inferences that might lead one astray from the simulation. It's a point one ought to keep in mind. Even though I'm really enamored by these calculations and everything, I always think we should keep a skeptical mind on the inferences one draws.
Okay.
Just to just to follow up on that point, some progress can be made by looking for asymptotic regimes where you can vary over the small range that's accessible to simulation, which won't solve the problem, but takes us at least in the right direction.
Yes, Wally.
I'll make some comments with the picture that you put on the board there, which I think is a bit of a different story, but it connects us back to how we started the conference, which is William Irvine's talk, beautiful talk. Unfortunately, he's gone now. So this is related to things we've done where you can study interactions in turbulent flow. There's this appeal of this helicity conservation, and it's possible to decompose the flow into, just like we talked about solenoidal and non-solenoidal, you can decompose the flow into helical of positive sign and helical of negative sign, which is what this picture relates to.
Yes.
And essentially, that's what he showed us on Monday. He's able to do in the lab. He can create helical initial conditions with his fancy experiments. And he verified essentially, although he didn't make the connection with this, that if you have helical turbulence, it inverse cascades even in 3D. And I think that's what he showed us with his knots. He started with all these complicated knots, and all these knots, what they want to do is undo themselves and basically go to large scales. We didn't address that. Probably something he should try in the experiment is when he shoots all these vortices to do his turbulent blob. Again, it's too bad that he left. But probably the best thing, again, this is part of the picture here, is if you want to have a forward cascade, probably the best way to do that is to try to have positive helicity crashing into negative helicity. So you should probably shoot helical vortices of different signs and try to create his turbulent blob in the middle. Right now he's just shooting neutral helicity vortices, but he could try to shoot a positive helicity meeting a negative helicity blob and creating a turbulent blob in the middle. So that's what this picture is about, but it's pretty far from the oceans and from the large scales and from the Nastrom and Gauge spectrum. But it connects back to the original talk that we had, the first beautiful talk that we had on Monday morning.
Except that there is also some new approach, not new approach, but kind of a non-conventional approach, qualifying turbulence like real turbulence having dimension bigger than 2 but smaller than 3. And in the theory which we have for rotating turbulence, I didn't go through this, but maybe I should mention it. If you look just on Kolmogorov turbulence on a small scale part, it looks like anisotropic Kolmogorov turbulence. But when you go to the rotation part, there is an equation which relates longitudinal and transverse structure functions with the dimension of space. And there is an analytical expression between structure functions for dimensional of 2 and 3 if spectrum goes with, say, exponent of n to minus 3. So the ratio is equal to 2 for 3-dimensional turbulence and equal to 3 for 2-dimensional turbulence. And from the theory which we get is somewhere in between, 2.6. So it appears kind of, you can give it interpretation, that rotation renders turbulence somewhere in between dimension 2 and 3, and then you have some problems. I mean, then you can have direct and inverse cascade in the same flow. So it's nobody we can discuss this possibility that formally the flow may be in intermediate direction. It's a dimension. It's not that trivial, but it's also interesting aspect which can be investigated. Yes.
Just to bring it back to triad interactions, I just wanted to note that Blakesley actually did some well-known and pioneering work on this in 2009, where she looked at the bispectrum of turbulent box simulations, and that work averaged over the opening angles of the triangles. And recently, she and I, with some collaborators, extended that to look at the full information on the triangles, including the angle dependence.
Mhm.
And we found that different physical conditions like magnetic fields and pressures have lots of signatures. So I just wanted to say, if anyone's interested in studying in simulations the triads or three-point function or bispectrum, we have code for that we would be happy to let you use. And in fact, I think it's already on GitHub, so find me or Blakesley, and we would be interested to talk further.
Okay, it's good to know. Do we have a...
Well, there's no more comments. How about we go eat lunch?